Hi everyone! In the last lesson, you learned how to write long sums using a concise notation. In this lesson, you'll learn how to actually calculate some of those long sums in no time at all, starting with arithmetic series. Let's get started. First things first, what is a series? Well, it's certainly nothing new to you. A series is just the sum of terms in a sequence. You spent the entire last lesson dealing with series and you didn't even know it. There are many types of series, depending on how the terms are generated. In this unit, we'll focus on series of terms generated from arithmetic and geometric sequences. An arithmetic series sums up terms generated with an arithmetic sequence. And a geometric series is a sum where the terms are generated from a geometric sequence. Series found in the real world typically involve a lot of terms, and it's not exactly a great use of anybody's valuable time to write all those terms out, which is why we just use summation notation for most series instead. In fact, some series are so long that summation notation is the only way to write them. For instance, here's an arithmetic series based on the arithmetic sequence with initial term of 1 and a common difference of 1. Would you want to expand this? Probably not. It has 100 terms to add together. Imagine having to write out 1 plus 2 plus 3 plus 4 plus 5 plus 6. Mia, a little help? Thanks, Mia. Even with a calculator, adding all these terms together would take a while. And way back in the day, you couldn't even use a calculator. You had to do all this addition by hand. Some teachers would give this exercise to their students so they could take a nice long break in the meantime. One time, a kid named Carl Friedrich Gauss interrupted his teacher's break after only a few seconds, raising his hand to answer 5,050, which was actually the correct answer. But how had Gauss solved it so quickly? While his classmates had been getting to work on the arduous task of adding 100 numbers together, one by one. Gauss had been more concerned about the long paper trailing off his desk and onto the floor. He hadn't wanted the paper to get stepped on, so he had picked it up off the floor and folded it into a neat stack on his desk. Now to get started working, he'd thought, and then hey, wait a second. Eureka! That's it! Gauss had immediately known what to do after that. Do you notice anything special about the terms that line up on his paper? Each pair adds up to 101. Using this information, can you figure out the rest of Gauss's strategy? Pause now and try to recreate his method for adding up the numbers from 1 to 100. Remember, the final answer is 5,050. We can assume that every pair will add to 101, so the only question is, how many pairs will there be? If we fold 100 terms in half, we get 50 terms on one half and 50 on the other. So there are 50 pairs, each totaling 101. 101 times 50 is 5,050. Carl Friedrich Gauss taught us that arithmetic series don't have to be long and tedious. You just need a good strategy. But then that raises this question. Would this strategy work for other arithmetic series, or just this one? Let's change our series to something more complicated. The series from term 3 to term 56 of the sequence, 5 plus negative 3 times n minus 1. Take a moment to find the first 3 terms in the series, then skip to the end and find the last 3 terms. The series starts with the third term, which is -1, and it will end with the 56th term, which is -160. We still have 4 terms to find here, but no evaluation is needed because we already know the pattern. Subtract 3 for each consecutive term. -1 minus 3 is -4, minus another 3 is -7. From the last term, we actually need to work backward by adding 3 to get the previous 2 terms. So we get -157, then -154 for the third to last term. Now that we've got a few terms on either end of the series, pause the video and test whether Gauss's method will still work. You should have found that, just like with the previous series, each pair of folded terms has the same sum, -161. How many of these pairs are there? Since we start on term 3, terms 1 and 2 of the sequence were left out of this series, so there are only 54 terms. If we fold the series in half, we get 27 pairs, each totaling -161. So the total sum for the series is -161 times 27, or -4,347. Gauss's method seems to work for all arithmetic series. But why? -1 plus -160 is obviously -161. If we move to the next term from this end, we can treat -4 as just being the initial -1 minus 3, and that will be paired with -157, which is just -160 plus 3 to back it up by one term. What happens when we add these expressions together? What will happen with the next pair of terms? Pause and reflect in your guided notes. The plus 3 and minus 3 end up zeroing each other out, so it's just -1 plus -160 again. This happens with every pair. The 10th pair is -1 minus 3 9 times, plus -160 plus 3 9 times, causing all those plus 3's and minus 3's to zero out. That leaves just -1 plus -160, resulting in the same total as any other pair, -161. So, this method will work for any series where the terms have a common difference. In other words, it works for any arithmetic series. We call this pairing strategy the arithmetic series formula. The final sum of a series with n terms is equal to half the number of terms times the sum of the first and last terms in the series. Here, I'll give you some new series to practice on. Pause the video now and try finding the final sum of these series using the arithmetic series formula. Then come back to check your answers. Let's check your answers and see how you did. In order to use the arithmetic series formula, we need to know the number of terms, first term, and last term. The number of terms in this series depends on the lower and upper limits. If we start at term 1 and keep going until term 20, that's 20 terms. We can also find the first term in the series easily. This series starts at term 1 of the sequence. In other words, the initial term, which is right here. The last term in the series will require a bit of math to find. It will be the 20th term in the sequence, so let's substitute 20 for the index of summation, then evaluate. And the 20th term, the last term in this series, is 43. Now that we have the 3 necessary pieces, we can use the arithmetic series formula. The final sum of this 20-term series will be half of 20 times the sum of 5 and 43. Half of 20 is 10, and 5 plus 43 is 48. and 10 times 48 is 480. Now that we've gone over number 1, take a moment to check your work for numbers 2 and 3 if you want, and then I'll go over those as well. For number 2, there are a total of 50 terms, with the first term in the series being 12 and the last term being negative 331. If we substitute those values into the arithmetic series formula, we get negative 7,975. For number 3, we're summing up 39 terms starting with 28 and ending with 1,434. The arithmetic series formula tells us that this sum is 28,509. See? With the arithmetic series formula, we can find the total of any arithmetic series in no time without a bunch of work. All you have to know is the first and last terms in the series and how many terms are included. But deducing the number of terms can sometimes be tricky, like with these examples. Pause now and try to determine how many terms are included in each of these series. Here are the actual amounts of terms. Let's use this one as an example. Sure, we could easily check this one by listing the terms from term 90 to term 93, but most series aren't this short, so we don't want to rely on this method. Instead, think about what the lower limit tells you. If the series starts at term 90, that means the first 89 terms of the sequence were excluded from the series. So the amount of terms is 93 minus the amount of excluded terms. This will work for any series. Take the upper limit and subtract the number of terms that the lower limit excludes. Here's another instance where deducing the number of terms can be tricky. Why is that? Instead of writing out this entire long sum, we've skipped to the end, which means we don't know how many terms are in the middle. We can clearly identify the first and last terms in this series, but we can't use the arithmetic series formula without knowing how many terms there are. But that's okay, because we can deduce the number of terms from what we already know. First, let's determine the explicit formula for the sequence. The initial term is negative 24, and this seems to be an arithmetic sequence with a common difference of 42. Now that we know the explicit formula, we need to figure out what value of n generates that last term, 1,320. To do that, we can substitute the nth term with that last term in the series, then solve for the term number n. Go ahead and work that out now in your guided notes. When we solve for n, we get 33, so 1,320 is the 33rd term of this sequence. Now we know how many terms there are and can use the arithmetic series formula. The total sum comes out to 21,384. Now it's your turn. Pause the video and try to find the total sum for these arithmetic series. Then come back when you're ready for the answers. For this first series, we need to find the last term. By substituting 62 into the explicit formula and evaluating, we find that the 62nd term is negative 171. This series also doesn't start at term 1, so we have to take into account that the first 14 terms have been excluded, meaning this series only has 48 terms. Now we've got everything we need, so we substitute everything into the arithmetic series formula and find that the series has a total sum of negative 3,696. The second series starts with 24.2 and ends with 373.8, but we don't know how many terms there are. We can find out by setting the sequence formula equal to that last term, then solving. In this sequence, 373.8 is the 39th term. Using the arithmetic series formula, we find that the final sum of this series is 7,761. Great work! Let's take a look at our key takeaways for today. Today you learned that an arithmetic series is a sum of terms in an arithmetic sequence, and how to quickly find the final sum of a series using the arithmetic series formula. You also learned how to deduce the number of terms when the series doesn't start at term 1, or when the terms in the middle of the sum have been skipped over to save space. Make sure to complete the additional practice after the guided notes, then check out the activity in which you'll explore some arithmetic series that you can find in the real world. After that, you'll be ready to complete the online practice and move on to the next lesson, where we'll play around with geometric series.
Hey, hey.